Okay, so this is it. So this is the fixed point. So when we displace it through an angular displacement theta, this distance from the mean point. This is the displacement, y. So the distance from the mean point to the mass is the displacement y. Okay. I said that theta for simple harmonic motion, theta must be very, very small. Theta must be very small. If it's large, if theta is large, it creates a non-uniform oscillation, which I'll talk about. Now, we seem to have, as we demonstrate these things, the forces acting on the string, we see the tension in the string tilting at an angle theta. So when we extend the vector, the weight vector in the opposite direction, we have this angle alternating with this. So if this is theta, this is also theta. So we more or less have the weight, the tension in the string acting at an angle theta. So this is T. And then the angle of tilt is this. Okay. So because of this tiltness, we want to resolve the tension T, which is tilted at an angle, to its vertical and horizontal components. And if we follow triangle law of vector addition, this will be its horizontal component, the adjacent to the angle. There's the angle, so there's the adjacent. Once we have the adjacent, a line drawn which is perpendicular to the adjacent gives us the opposite. So once we have located the adjacent, the opposite or vertical must be perpendicular to it to form or to obey triangle law of vector addition. So this plus this component plus this component must be equal to T. So we are interested in the adjacent. Okay, T adjacent, TA. Obviously, the adjacent will be equal to, when we take cosine of the angle, cos theta. This is at the adjacent, which is TA over the hypotenuse, which is the tension in the string. So TA is equal to T cos theta. So this horizontal component of the tension is equal to T cos theta. Now, what is the vertical component? Let's indicate that to be TV. So TV, T vertical, when we take the sine of this, sine theta is equal to TV over T. And therefore, TV is equal to T sine theta. Class, I hope you are following me. Are we following?
Yes, sir.
Good. So ideally, this is the adjacent, it's supposed to be here, but vectors are equal no matter where they are, if they have the same magnitude, direction, and they are parallel. So instead of writing the vertical component of the tension here, we are bringing it here. Okay. Oh, hold on. I think I'm rather looking at conical pendulum, which are very, very similar. Hold on. The vertical component must not be here. Okay, so I want to extend this. It should be taken from this line rather. If we extend the tension, in the opposite direction, and then please mute yourself. If you just join us, mute yourself for me. This concept and conical pendulum, they are very similar. So if you are not careful, you use conical pendulum. So this is mg. Now this is equal to this vertically opposite angle. So if this is theta, this is also theta. And if you are measuring the size of this angle, you put your protractor zero line on this line, okay, making this line the adjacent to this. So this would become the adjacent, whereas, so when you identify the adjacent, a perpendicular line drawn from the adjacent becomes the opposite. So opposite, this is the adjacent, and by triangle law of vectors must be equal to this. So when we resolve this side, the opposite will be equal to mg sine theta. Under this concept, the horizontal would also be mg cos theta, meaning the weight is tilted at this angle theta. So we are resolving the weight to get its vertical component and horizontal component. Okay, similar to what we did here. But if you resolve the tension, it is in a situation of conical pendulum. So here we resolve the weight into vertical and horizontal component. Now, because of equal vectors, instead of having the opposite over here, we are bringing it onto the mass. Vectors are equal no matter where they are. So mg sine theta component, which is also equal to this, instead of what we have here, is being brought onto the mass, because vectors are equal no matter where they are if they have the same magnitude, direction, and are parallel to each other. Now, if we look at the forces on the mass, the tension T within the strength is balanced by mg cos theta. Okay, so there is a net force of 0 vertically. But if we look at horizontal forces, okay, if we look at horizontal forces, mg sine theta is unbalanced, meaning there is no force in the opposite direction which balances it. So the mg sine theta component is unbalanced. And the unbalanced force is always equal to the force which always tries to restore it to its original position or the equilibrium position. So when, for a simple pendulum, when you displace it at an angle, it will be oscillating back and forth, to and fro, okay? Meaning when it gets to this point, let me draw something too. If the mass comes to this point, there's a force which is pulling it to come back to the mean point. This is a fixed point. When it crosses and then come to this point, there is also a force which is always trying to restore it to its fixed point. So the force which always does this is equal to the mg sine theta component. So for a simple pendulum, the restoring force for a simple pendulum, for the motion of a simple pendulum Isaac Atta, please mute yourself. For the motion of a simple pendulum, the restoring force is equal to mg sine theta component of the weight. It is also similar to a banked road. On a banked road, what provides the centripetal force has always been the r sine theta component. Okay, for a motion of a simple pendulum, the restoring force, F restoring, is always equal to mg sine theta component of the weight. Okay, that is what at every time restores the object back to its mean point. So what it means is that the moment you displace the pendulum bob at an angle theta, at that small angle, when it comes to any extreme, there is a restoring force which is always restoring the object back to its original position or the rest position, whose value is equal to mg sine theta. When it comes here, it will cross the fixed point because of its momentum and come to the other extreme, and there is always a restoring force directed towards the mean point. Are you okay? Please, class, are we okay?
Yes, please.
All right. Now, the next task is to show that this motion is simple harmonic, and we have a simple pendulum, and we have studied the conditions for simple harmonic motion. One, the acceleration must be directly proportional to the displacement. The motion must occur at a constant or uniform angular velocity, and the restoring force must always be directed to the fixed point. And that is what we have seen. This is one of the conditions which we have identified. So the next is to show that this motion has uniform angular velocity, and also to show that the acceleration is directly proportional to the displacement. Now, from Newton's second law, F is equal to ma. Every acceleration is caused by an external force. So the external force which actually causes the acceleration is equal to this. In our case, it's equal to mg sine theta. So we equate mass times A by the restoring force, F restoring. So ma is equal to mg sine theta. Okay. Masses will cancel out. Masses will cancel out. And so we have the acceleration A equal to g sine theta. If we look at what we have, we realize that sine theta is equal to the displacement y over the length of the string L. Sine theta from the right angle triangle we have here. Sine theta is equal to the displacement y over the hypotenuse, which is the length of the string. Please, here we are looking at length. That is why we are ignoring the tension in the string. So when we substitute this, we have acceleration is equal to J times y over L. This acceleration A is negative. This is because for a simple harmonic motion, the acceleration is always opposite to the displacement. So the displacement is y. So where y equals displacement from the mean point. Displacement from the mean point. Therefore, we have A is equal to negative J over L times Y. Now the ratio G over L is equal to a constant. This is a constant because G is gravity, acceleration due to gravity. Then L is the constant length of the spring. Here, if you have no idea of what the length is, you can still measure to determine it. Okay, so it is of this reason that the ratio G over L is a constant. So if this is a constant, then we can say that A is equal to negative K, which is the constant, is equal to the displacement y. And so we've managed to prove that acceleration is directly proportional to the negative of the displacement y. So by this, we managed to prove that for the motion of a simple pendulum, its acceleration is always directly proportional to the displacement y, which is a second satisfaction to conditions necessary for a body to execute simple harmonic motion. So the first one is this, and the second one is what we have just determined or derived. Please, if you have any question, ask. Is there any question? Or if there is any explanation you want me to add to what I've done, do that whilst I take notes of attendance. Okay. Are we all okay with the explanation so far?
Yes, please.
Okay. A minute.
Recording in progress.
Okay. All right. So for the motion of a simple pendulum, its acceleration A, the acceleration of the motion of a simple pendulum is equal to A is equal to minus J over L times the displacement Y. There's the acceleration of a body executing simple harmonic motion. Okay, where J over L is equal to a constant K. Constant K because, yes, J is acceleration due to gravity, but L is the constant or always knowing length of the string. So that makes the ratio G over L constant. Therefore, A is equal to negative K times Y, which satisfies the simple harmonic motion. So this satisfies simple harmonic motion because the acceleration is directly proportional to the displacement and oppositely directed. Let's look at the period of oscillation. Oscillation of a simple pendulum. And we know period capital T to be the time taken by an oscillating body to make one complete cycle. So if a body is oscillating, how do we determine the period? For an oscillating body, a complete oscillation is made up of 4 parts, 4 equal parts. So when a body is oscillating, and then you displace it from the equilibrium position. Its path is, it will move from the mean point or fixed point to one extreme, so 1. This is the first part. The second part is to move from the extreme back to the mean point. This is 1. Then the third part is that the oscillating body will come to the other extreme again. So 1, 2, 3, and back to where it started. Okay, so 1, we moved it from the mean point when it was at rest. 1, 2, 3, back to wherever it starts. So whenever it comes back to where it was moved from, or where it was initially moved, we have a complete cycle. So when it's here and you move it here, 1, 2, 3, 4. Or usually we take it from when you move it from here and then returns back to where it was taken from, we have a complete cycle. So we are moving it from the right half, and when it comes back to the right again, 1, 2, 3, 4, 5. And in our practicals, we usually count the number of complete cycles. So note, you do this in practical, so note how to do the counting. Okay, let me start again. When you displace it through small angle, so I'm moving it, it was here, moving it to this end. You must go and come to give me 1. So 1, 2, 3, 4. Okay, so you end at the number of oscillations given to you. Usually we count and time it for 20 oscillations. Now, the reason why we have to count for that number of times is that we want the time taken for a complete oscillation 1. But when we just count it once, we may not be accurate with our timing. So when you are moving it, the moment you displace and leave it, you must start the stopwatch 1. But we may not be accurate. So what we say is that, okay, let us count a certain number of oscillations, determine the total time for that number of oscillations, and to get the period, we divide it by the number of oscillations. So all that we need is that we want the time for 1, moving from one extreme and back. But because we cannot be accurate in our timing, okay, what we say is that let's count and time for 20 or 10. So 1, 2, 3, 20 or 10 times. Then we can determine the time taken to make one complete oscillation by dividing the total time we have for the 2010 by that number of oscillations. This would enable us to be, or will help us to be accurate. So that is basically the reason why we count that number of times, for accuracy or precautionary sake. Class, are we okay?
Yes, sir.
All right.
Yes, sir.
So let's quickly look at the period of oscillation of a simple pendulum. How do we do it? Theoretically. Practically, we must count it time for a certain number of oscillations and divide the total time by the number. But theoretically, there's also a way to go about this. Now, the acceleration formula for a body executing simple harmonic motion is equal to negative omega squared times the displacement y or x. This is general acceleration formula. Acceleration formula for SHM. And the acceleration formula we have for a simple pendulum, we had A is equal to minus J over L times Y. When we compare, we can clearly see that omega squared is equal to J over L. And we have omega giving us the square root of J over L. Okay. Omega we know to be equal to 2 pi over the period. So when we substitute 2 pi over the period, we have this being equal to root of J over L. Class, help me make T the subject. Help me make T the subject. I'm waiting for you to help me out here. Let's make T the subject from what we have there.
T is equal to 2 pi root of L over G.
Okay, thank you. So we have this, I'm coming in. I'm loading attendance again. Some of you have joined, so I need to update attendance. Else your parents may think you never came. All right. So T is equal to 2 pi. Okay, so you are right, but let me quickly go through it with you in order to, help those who perhaps were not able to do that. So 2 pi over the period is equal to root of G over L. And my interest is to make T the subject. So when I take the reciprocal of the left-hand side, I must take the reciprocal of the right-hand side. But note that the right-hand side is also equal to root of G over root of L. So when I reciprocate the left-hand side, I'll have T over 2 pi. And so in mass, I must do the same thing to the right-hand side. And I'll have root of L over root of G, which is also equal to square root of L over G. Then once I'm looking for T, I multiply 2 by 2 pi to eliminate that. So I have T is equal to 2 pi times the square root of L over G. And this is the period of oscillation of a simple pendulum. Of a simple pendulum. As science students, how to derive this must be at your fingertips. By this equation, the period for an oscillating body, its period is directly proportional to the square root of the length. Meaning, when the length increases, the period would also increase. And the period T is inversely proportional to the square root of G. But on the surface of the earth, that will not affect us, because on the surface of the earth, G is constant. Okay, so for two different lengths, there must be two different periods. So T1 is directly proportional to root of L1. T2 must be directly proportional to root of L2. Therefore, T2 over T1 or T1 over T2 must be equal to square root of L2 over L1. On different planets where gravity varies, it also means that T1 must be inversely proportional to root of gravity 1. And T2 must be inversely proportional to 1 on root of gravity 2. So if you take T2 over T1, it must give you square root of G1 on G2. But this is period on different planets where gravity varies, but on the surface of the earth, because G is constant, it does not affect us. Please, are you okay?
Step is it supposed to be G2, J1 or J1, J2?
I'm sure it will be G1 on G2. We can go through it. So if we are looking for T2 over T1, then we are talking about 1 over root of G2, okay, times root of G1 over 1. So I'm right. Because you divide by 1 over root of G1. And when you change the division sign to multiplication, you must invert it. Are you okay?
Yes, please.
So class, if you have a simple pendulum and the length is doubled, let me create a question for you. For a simple pendulum, of length L and period T, what will be the effect on the period when the length is doubled. Yes, make me proud. So, for a simple pendulum of length L, what will be the effect on the period when the length is doubled? So 5 minutes, make me proud. Are we through? Hello, are we through? Jojo and Co, are you through? Hey, can you hear me? Class, can you hear me?
Yes, please.
Jojo, what's your answer?
Please, period 2 is also double.
I doubt if it will be double. Elizabeth, what's your answer? Okay, so we are talking about for length L, the period is T. Let's even do that for, let L be equal to a period of T1. Now, when the length is doubled, twice of L, T2, we don't know. And that's what we are looking for. So we just realized that T is directly proportional to root of L for the same string. For the same string of constant G, once the concentration is on the surface of the earth, of course, G will be constant. So if T is directly proportional to this, then T1, Jojo,
So I said I got it was that root of 2t that I got, not double of t.
Exactly. So T1 must be directly proportional to root of L. Then T2 must also be directly proportional to root of, this is L1, L2. But L2 is twice of L1. So when you take T2 over T1, this must be equal to root of L2 over root of L1. Meanwhile, L2 is equal to 2 times L1 or L. Therefore, T2 over T1 is equal to square root of 2L over L. And the second period will be equal to root of 2 times T, the period when the length is L. Okay? So it means that when you increase the length, if you double the length, the new period T2 will be equal to square root of 2 times the first period, or 1.414 of this. So this is what will happen if the length is double. Now, what will happen if the length L is tripled? What will happen to the period when the length is tripled? Yes. Same concept.
This will be root of 3 times the period.
Hello, come again.
Please, it will be root of 3 times the period.
Yes, the initial period. So T2 will be equal to root of 3 times T1 or T. So that's it. All right. Let's all right. Please put this question down. Calculate the period of oscillation. Calculate the period of oscillation and the time for 20 oscillations. Calculate the period of oscillation and the time for 20 oscillations of a simple pendulum calculate the period of oscillation and the time for 20 oscillations of a simple pendulum I of length 100 centimeter. I of length 100 centimeter. And then II of length 90 centimeter. Take G, take gravity, acceleration due to gravity to be 9.8 meter per second squared. Take G to be equal to 9.8 meter per second squared.
Mr. Edia,
Hello.
please can you go over the question?
Calculate the period of oscillation and the time for 20 oscillations of a simple pendulum I of length 100 centimeter, I of length 100 centimeter, I of length 90 centimeter, I of length 90 centimeter, I of length 100 centimeter. Take J to be equal to 9.8 meter per second squared.
Thank you.
Welcome. Time is not on answer. So T, we know T to be equal to 2 pi root of L over G. So if L is equal to 100, then the period would be equal to 2 pi over 100, which is the same as 1 meter divided by 9.8. So here, if you are using the formula, when you are given a length, then you must change the length from centimeter to meter because acceleration due to gravity is given to you in meter per second. So SI units. And when you do that, I think the period will be for a length of 100 centimeter, the period will be close to 2.0 seconds. Okay, and the time for 20 oscillations, don't forget the same period. Okay, so yeah, all right. The same period is equal to total time over number of oscillations. So the time for that number of oscillations will be the period, which is 2 seconds, divided by total time, which we are looking for, over 20. Therefore, T total time will be equal to around 40 seconds. For when L is 100, II, when L is 90, when L is 90 centimeter is the same as 0.9 meter. So here the period is going to be 2 pi times 0.9 divided by 9.8. And the period will be close to, this is 1.9 seconds. And the total time for 20 oscillations would be equal to the period times the number of oscillations. So 1.9 times 20 oscillations. And this would give us around 38.0 seconds. How many of you got everything correct? Show by hands. If you had all calculations correct, let me see you and award you. Oh, okay. All right. Thank you. You'll be rewarded so that I'll later, if okay, your hand is up because of it. You'll be awarded so that you later reward me. Last question, then we move on. Calculate or determine the period of oscillation of a simple pendulum. If the initial length is increased by 50%. So if the initial length L is increased by 50% of the initial, of the original value, so the new length is equal to 50% increment of the initial length. Okay, so determine the period when the initial length is increased by 50%. Let's see how that would affect the period. Are we through? Hello, are we through? Okay, so this time around, we are only saying that the new length L2 is equal to 50% plus the original length. The length is increased by 50%. So in all, the new length will be equal to 150% of the original length. L2 will be 150% of the original length. Okay, we are increasing it by that. Or L2 can also be equal to 50% S 0.5 L plus the original length. And so this will also give us 1.5 of L. And don't forget, 150% is the same as 1.5. Okay, so either you express it in percentage or this. So T2 on T1 would be equal to square root of 1.5 of L over L. Therefore, T2 would be equal to root of 1.5 of T1. This will be the new period. Please, is it understood?
Yes, sir.
Okay, so these are the simple. Usually when you understand it and they talk about these percentages, you can easily do it. Now, if T is equal to 2 pi root of L over G, then we can also express frequency. Our frequency is 1 over F of the period. Our period is 1 over F of the frequency.
Yes,
So
please.
we can also express the same thing as 1 over 2 pi times G over L. Okay. All right. If you have any question, ask. This is the motion of a simple pendulum. Let's look at the motion of a loaded spring. The motion of a loaded spring. Springs are used for so many purposes. Okay. Let me see if I have spring around. So if you haven't seen a spring before, I'm going to show you one. Hey. So this is a spring. Please, can you see?
Yes, sir.
This is a spring. And so this is unloaded, the kind of spring where nothing has been connected or suspended. Okay. Now, if you suspend something on the spring, unloaded spring, when you load it, then it would extend. Okay, it will extend. So suspending a load on this, suspending the load on this is what we are calling as loaded spring. The moment the load is connected to it, it will stretch it. And so it becomes a loaded spring. This is unloaded spring and then a loaded spring. So we are saying that the motion of a loaded spring is simple harmonic. We are going to investigate, look at it, because if a motion is simple harmonic, one, we must see that its acceleration is directly proportional to its displacement, and the restoring force must always be directed to the fixed point. All right. Okay, so let's go back to our board and then look at what goes in there. So the motion of the loaded spring. An unloaded spring so this is the spring attached to so this is unloaded spring A. Then, so if it's unloaded, this horizontal or broken line represents the fixed point. So when we load it, that is suspend a load or a mass to it, this is the weight of the spring. The moment you load it, it would stretch by some amount. And so this distance becomes the extension y or x. So when there is no mass, this is the fixed point or the equilibrium position. The equilibrium position is what I've indicated with broken line. So equilibrium position. Now springs are such that the moment you put a load, it will be oscillating back and forth. It will be moving up and down about this point, the equilibrium position. So repeated up and down movement of it. Okay, and this is what I mean by it will be oscillating back and down when you suspend a load. It's unfortunate I don't have any load here. Okay, it will be oscillating back and down around the equilibrium position. So suspending the load will stretch it by this amount. Okay, and so it will be moving up and down about or around the pen, which is the equilibrium position. Now, springs work on Hooke's law. Springs work on the principle of Hooke's law. And Hooke's law Principle of Hooke's law. Hooke's law says that provided the elastic limit of a material, okay, provided the elastic limit of a material is not exceeded, the extension is directly proportional to the displacement. So provided the elastic limit of a material is exceeded, the extension is directly proportional to the load or the force on the material. And Hooke's law is given by the equation F is equal to minus Kx. F is equal to minus Kx. Let me clear this part and continue. So F is equal to negative Kx, where F is equal to the load or force and K is equal to the spring or force constant. And X is equal to the extension. So in what we've done, our extension is actually Y. So instead of X, let's use Y to suit what we have. Okay, this is Hooke's law. So for springs, when you suspend a load, it will stretch it, and that's the extension. And springs are always such that the restoring force is always directed to where the mean point is. So when you stretch it downwards, it would always try to restore its shape originally to the direction of the fixed point or the equilibrium position. So the restoring force would act in the opposite direction. And this is what I mean. You see, look at what I have. When I extend this and leave it, this position is the equilibrium position when it is at rest. Okay? But when I stretch it, and leave it, it is always trying to restore back its original length or position. And so there's always a force directed to where the restoring force, the equilibrium position is. Please, the equilibrium position is the pen, the pen. So when I stretch it and leave it, it is always coming back to where the equilibrium position is. And so the restoring force acts in the direction of the equilibrium position. Please, are we okay? Are we okay?
Yes, sir.
Okay. So this restoring force is equal to Hooke's law. The restoring force which restores the object's original state or position is equal to Hooke's law, or is equal to K times Y. So F restoring is equal to minus K Y, Hooke's law. And it's negative because the displacement, the extension, which is the displacement Y, is opposite to the direction of the acceleration or the restoring force. Okay. So if the restoring force is equated to Hooke's law, then what will be the acceleration? Because for every force, there must be an acceleration. So we want to determine the value of the acceleration. And from Newton's second law, every force or every acceleration is caused by a force and is given by F is equal to ma. So we equate ma to minus ky, which is the extension. And because you are looking for the acceleration, make A the subject. A is equal to negative K over M times Y. Now, M is the mass of the load attached. And K is the spring constant. So where M equals mass of the load and K is equal to the spring constant. And Y is equal to the extension, or technically we can also say the displacement. Instead of Y, if you see an X, is the same thing, okay? Now K, the value of K, the spring constant or the force constant, determines how stiff or loose a spring is. Can I move on to the next page, class? If you are done writing.
No, please.
All right, then be snappy.
Please, you can move now.
Okay. So the spring constant K determines how rigid or loose springs are. So if the spring is very rigid, so strong, as in what is used in car shock absorbers, the value of K is high, very large. If the spring is so loose, example, as in the slinky spring, slinky, the value of K is less. So the value of K determines how rigid or loose springs are, okay? So we have the acceleration of a loaded spring equal to minus K over M times the extension Y. And since this ratio K over M, because K is constant, spring constant, it measures how stiff or loose springs are. And M is also the fixed mass of the load attached to the spring. Then we can say that this ratio K over M is a constant. And if this is a constant, then we can say A is equal to a constant big K Y. And so we've managed to prove here that so big K is actually this ratio. We've managed to prove that, oh, the motion of a loaded spring, its acceleration is directly proportional to its displacement Y or extension Y and oppositely directed. So we have satisfied a condition for SHM. So if a motion is said to be simple harmonic, then you must be able to derive this relationship out of it. And so for a loaded spring or a helical spring, its acceleration E is equal to minus K over M times its extension within. Okay. So here too, we are interested in the period of oscillation of a loaded spring. Of a loaded spring. So we compare the acceleration of this to the acceleration of a general acceleration of a body executing simple harmonic motion. So comparing this, compare A is equal to negative K over M Y 2. A is equal to minus omega squared Y, the general acceleration equation of a body executing simple harmonic motion. And you could deduce that omega squared is equal to K over M. Out of this, we can say that the spring constant, if you are looking for the spring constant, it can be the product of the mass and then the square of the angular velocity. So do not overlook this. The spring constant K is equal to the mass times the square of the angular speed or angular velocity, omega. And further expand to get a period. Omega is equal to square root of K over M. And because period is also equal to 2 pi over T, then we can equate this 2 pi over T to square root of K over M. Please, class, help me make T the subject. Help me make T the subject.
T is equal to 2 pi root of M over K.
So T will be equal to 2 pi times root of M over K. Ladies and gentlemen, this is the period of oscillation of a loaded spring. Period of oscillation of a loaded spring. Meaning, the period of oscillation of a loaded spring is directly proportional to the square root of the mass, meaning when the mass or the load, mass of the load attached increases, this also increases. And the period is also inversely proportional to the root of the spring constant. This is at constant K. This condition holds when K is constant, and the second one also holds when M at constant M. So for two different masses, there will be two different periods. So T1 is directly proportional to root of M1, and T2 over T2 divided by root of M2. Therefore, T1 over T2 will be equal to the square root of M1 over M2. Similar to the simple pendulum. Then for masses, for spring constants, T1 will be inversely proportional to 1 over square root of K1, and T2 would also be inversely proportional to square root of K2. Therefore, T1 over T2 would also be equal to root of K2 over K1. So for different spring constant, this is how you can determine the period or the change in the period as well. Any question? Please, is there any question? All right. I'll give you 5 minutes for water break. Turn around or go and drink water and then come over. So let's go for this quick commercial break and we'll continue afterwards. 5 minutes. Okay. Our 5 minute water break is over. Hello, are you there?
Yeah.
Okay. So let's continue. Now, in fact, let's go back to simple pendulum and add this on. Usually, it will help. I think this will help those of you in NSMQ. For simple pendulum, especially the grandfather clock. The grandfather clock also works on simple pendulum because it is a metal string. The string is a metal, not thread, as we have, okay, as in this case. But then, if it is a metal string, temperature affects the period as well. For thread, we've just seen that the period is affected by the length. So when you change, as the length increases, the period must also increase. And as the length decreases, the period must also decrease. Okay. As for the other factor on which it depends is gravity. But gravity on the surface of the earth, that is constant. So we will not talk about gravity, effect of gravity whilst we are on earth, unless we are comparing different planets. But for pendulum strings made of metal string, okay, temperature also affects it. So temperature also affects the period when it is a metal string. Please take note of that. Not all the times, but temperature affects the period of oscillation when it is a metal string. Are you there? Jojo. Okay, so temperature also affects the period when the pendulum string is made of a metallic string or length or wire, as in the grandfather clock. And how does it affect it? You know, when L length of a string, is subjected to a change in temperature, delta T, the length increases by, the new length would be equal to the original length L plus the small change in the length. Okay. Linear expansivity of metal. So that small change in the length is also a product of coefficient of linear expansivity, then the original length, and the change in temperature. So that small change, where this is small change in length as a result of the temperature. Therefore, we are saying L2 will be equal to the original length plus small change in length due to temperature. Okay, so L2 would be equal to L1 or L plus the small change, which is equal to alpha L times the change in temperature. Please change in temperature here is equal to final temperature minus initial temperature. So therefore, this is the expression for the new length. So when the temperature changes, the length would also change. And we just noticed that period is directly proportional to square root of the length. So L1, initial length L, would give us a period which is root of L, where T and L are initial temperature and length respectively. Then when the length changes as a result of the temperature, we have T2 also being directly proportional to square root of L2. So when you take this ratio, the ratio of the length, and then the corresponding period, T2 over T1, this is equal to root of L2 over L1. Okay. Therefore, T2 over T1, when we substitute the change in the length due to temperature into this, we have L2 as L times 1 plus alpha delta T divided by L1 is the original length, which is L. Therefore, the new period will be equal to the original period times the square root of 1 plus alpha delta T, or 1 plus alpha delta T raised to the power half times the initial period, T2. And when we simplify this to the second term, we have just T1, T times 1 plus half alpha times delta T. All the other terms will be so small. So this is how the period will change for grandfather clock, whose string is made up of, or is made of metal, which can be affected by temperature. So this is for simple pendulum whose string is made of a metal or conductor, how temperature affects. So please note that T2 and T1 are periods of oscillation, not temperature. Periods of oscillation. If you are not careful, you can take it as a temperature. That's why I'm defining. And alpha is a coefficient of linear expansivity. Or linear expansion. And delta T is equal to change in temperature. Class, please, are you okay? Class, are we fine?
Yes, please.
All right, so this is how temperature affect the period of oscillation of a grandfather clock for let me indicate the heading here. So for the grandfather clock, whose string is a wire of length L. So if we have a simple pendulum whose length is made of wire, a metallic conductor, then the period is also affected by change in temperature delta T. Okay. Are you still writing? Or I can move on.
Please, you can move on.
Okay. So I think what we are led to do under this is we've done loaded spring, simple pendulum. So we are led with energy, the energy of a body executing simple harmonic motion, and we have discussed some parts of it. So in fact, I still owe you yesterday. I want to see if within the week by Saturday we can make time so that we can clear the arrears, finish it, so that by next week we can start a new area. Okay, we can start a new area. Please, if you have any question, quickly ask. If you don't have any question, then we end the lesson. Is there any question?
No, please.
All right. Then, bye-bye and continue. Please, if you haven't submitted your assignment, quickly do that because I'll be sending loads more under what we've done for today as well. So if you haven't submitted, okay, I'm still waiting. Bye-bye to all of you.
Bye.
Bye.
Okay.